Crouse-Hinds Type CH panel breakers are obsolete and no longer manufactured. Bryant panel breakers are compatible with Crouse-Hinds panels. Specifically, Bryant Type BR panel breakers and Bryant Type ERP panel breakers are options. Westinghouse panel breakers are also compatible with Crouse-Hinds panels. The Westinghouse Type DB panel breakers, Westinghouse Type DC panel breakers, and Westinghouse Type DF panel breakers can be used. It is important to consult the specific panel label or manufacturer's documentation to confirm the exact compatible breaker types for the particular Crouse-Hinds panel. Using incompatible breakers can be hazardous and may void the warranty or safety certifications of the panel. Some older Crouse-Hinds panels may not accept breakers from other manufacturers. The electrical panels are designed to distribute electricity safely and efficiently throughout a building. Breakers are a critical component, protecting circuits from overloads and short circuits. Understanding breaker compatibility is crucial for maintaining safety and preventing damage to the electrical system. Firstly, ensure the replacement breaker has the same voltage rating as the panel. Secondly, confirm the amperage rating of the breaker matches the circuit it protects. Thirdly, never install a breaker with a higher amperage rating than the wiring is designed to handle. This could lead to overheating and fire. Fourthly, visually inspect the breaker for any signs of damage before installation. Fifthly, turn off the main power before working on the electrical panel. Sixthly, use insulated tools to prevent electrical shock. Seventhly, if unsure about any aspect of the installation, consult a qualified electrician. Eighthly, always follow the manufacturer's instructions and local electrical codes. Ninthly, test the breaker after installation to ensure it is functioning correctly. Tenthly, label the new breaker clearly to identify the circuit it controls. Circuit breakers are overcurrent protection devices used to protect electrical circuits from damage caused by overload or short circuit. Their basic function is to interrupt current flow after a fault is detected. A circuit breaker is designed to protect an electrical circuit from damage caused by excess current from an overload or short circuit. It automatically interrupts the flow of electricity. Unlike a fuse, which operates once and then must be replaced, a circuit breaker can be reset, either manually or automatically, to resume normal operation. Circuit breakers are made in varying sizes, from small devices that protect individual household appliances up to large switchgear designed to protect high-voltage circuits feeding an entire city. The generic function of a circuit breaker, as an automatic means of removing power from a faulty system, is often abbreviated as OCT or overcurrent protection device. We should delve into the common types of circuit breakers, including miniature circuit breakers, molded case circuit breakers, air circuit breakers, and vacuum circuit breakers. Miniature circuit breakers, or MCBs, are thermal-magnetic devices commonly used in residential and light commercial applications, typically rated up to 125 amps. Molded case circuit breakers, or MCCBs, offer high current ratings and interrupting capacities and are used in industrial and commercial settings. Air circuit breakers, or ACPs, are used for high current applications, often serving as main disconnects in large electrical systems. Vacuum circuit breakers, or VCBs, are utilized in high voltage applications, providing rapid and reliable interruption of fault currents. Breaker tripping mechanisms are another key aspect of circuit breaker technology. There are two main types of tripping mechanisms: thermal and magnetic. Thermal tripping relies on a bimetallic strip that bends when heated by an overcurrent, causing the breaker to trip. Magnetic tripping uses an electromagnet that trips the breaker instantly when a high fault current is detected. Some breakers combine both thermal and magnetic tripping mechanisms for comprehensive protection. The interrupting capacity of a circuit breaker is the maximum fault current it can safely interrupt without being damaged. It is crucial to select breakers with an interrupting capacity sufficient for the potential fault currents at the installation location. A breaker with an insufficient interrupting capacity can fail catastrophically during a fault, posing a significant safety hazard. Circuit breaker standards and certifications are critical for ensuring the safety and reliability of these devices. Organizations like Underwriters Laboratories, or ALL, and the International Electrotechnical Commission, or IC, develop and maintain standards for circuit breakers. Compliance with these standards is indicated by certifications such as UL listing or IC marking. These certifications demonstrate that the breaker has been tested and meets rigorous safety and performance requirements. Furthermore, understanding the electrical panel itself is essential. The electrical panel, also known as a breaker box or load center, is the central distribution point for electricity in a building. It receives power from the utility company and distributes it to various circuits throughout the building via circuit breakers. The panel's main breaker controls the power supply to the entire panel. The panel also includes a neutral busbar, which provides a return path for current, and a ground busbar, which is connected to the grounding electrode system. Electrical panels are rated for a maximum current, which should not be exceeded. Overloading the panel can lead to overheating and potentially a fire. It's essential to ensure the panel has sufficient capacity for the building's electrical load. Electrical panels should be installed in a readily accessible location, free from obstructions. They should also be protected from moisture and physical damage. Regular inspections of the electrical panel are recommended to check for any signs of damage, such as rust, corrosion, or loose connections. Any issues should be addressed promptly by a qualified electrician. Now let's look deeper into some specific breaker types. Ground fault circuit interrupters, or GFCIs, are designed to protect against ground faults, which can occur when current leaks to ground. GFCIs are commonly used in bathrooms, kitchens, and outdoor locations where there is a risk of exposure to moisture. Arc fault circuit interrupters, or RFCIs, are designed to protect against arc faults, which can occur when damaged or deteriorated wiring creates an unintended electrical arc. RFCIs are typically installed in bedrooms and other areas where there is a high risk of fire. Dual-function breakers combine the protection of both GFCIs and RFCIs in a single device. These breakers are becoming increasingly popular as they provide comprehensive protection against both ground faults and arc faults. Surge protective devices, or SPDs, protect electrical equipment from voltage surges caused by lightning strikes or other electrical disturbances. SPD are typically installed at the main electrical panel to protect the entire electrical system. It's important to note that circuit breakers have a limited lifespan and should be replaced periodically, typically every 25 to 30 years. Over time, breakers can become less reliable and may not trip properly in the event of a fault. Replacing breakers is a relatively inexpensive way to maintain the safety and reliability of the electrical system. In addition to replacing breakers, it's also important to periodically inspect the wiring in the electrical panel. Look for any signs of damage, such as frayed insulation, loose connections, or corrosion. Any damaged wiring should be repaired or replaced by a qualified electrician. When working with electrical panels and circuit breakers, safety should always be the top priority. Always turn off the main power before working on the panel. Use insulated tools to prevent electrical shock. Wear safety glasses to protect your eyes. If you are not comfortable working with electricity, hire a qualified electrician to do the work. Incorrectly installed or maintained electrical panels and circuit breakers can pose a serious safety hazard. They can lead to electrical shock, fire, and other injuries. By following proper safety procedures and consulting with a qualified electrician, you can ensure the safety and reliability of your electrical system. Moreover, consider the impact of voltage drop in electrical circuits. Voltage drop is the decrease in voltage that occurs along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can cause equipment to malfunction or fail. Voltage drop can be minimized by using larger conductors, shortening the length of the circuit, or reducing the current flow. Voltage drop calculations are essential for designing electrical circuits that operate efficiently and reliably. To calculate voltage drop, you need to know the conductor size, the length of the circuit, the current flow, and the conductor's impedance. There are several online voltage drop calculators available that can simplify this process. The National Electrical Code, or NEC, provides guidelines for maximum allowable voltage drop in electrical circuits. These guidelines are intended to ensure that equipment operates properly and safely. Understanding voltage drop is crucial for designing and maintaining electrical systems. Regarding electrical safety, it's important to understand the concept of grounding. Grounding is the connection of electrical equipment and systems to the earth. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip circuit breakers and prevent electrical shock. Grounding also helps to stabilize voltage and reduce electrical noise. The grounding electrode system typically consists of a ground rod, a ground plate, or a metal water pipe that is buried in the earth. The grounding electrode system is connected to the electrical panel via a grounding electrode conductor. All metal enclosures of electrical equipment must be grounded to ensure that they are at the same potential as the earth. This helps to prevent electrical shock in the event of a fault. Ground fault circuit interrupters, or GFCIs, are designed to protect against ground faults, which can occur when current leaks to ground. GFCIs are commonly used in bathrooms, kitchens, and outdoor locations where there is a risk of exposure to moisture. GFCIs work by monitoring the current flowing in the hot and neutral conductors. If there is a difference in current, it indicates that current is leaking to ground. The GFCI will trip the circuit breaker, cutting off the power and preventing electrical shock. In addition to grounding, bonding is another important safety practice. Bonding is the connection of all metal parts of an electrical system to ensure that they are at the same potential. Bonding helps to reduce the risk of electrical shock and fire. Bonding is typically accomplished by connecting all metal enclosures, raceways, and equipment to the grounding electrode system. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. These requirements are intended to ensure the safety of people and property. It is important to follow the NEC guidelines when installing and maintaining electrical systems. Now let's explore some advanced topics in circuit breaker technology. Solid-state circuit breakers use electronic components to detect and interrupt fault currents. Solid-state breakers offer several advantages over traditional electromechanical breakers, including faster tripping speeds, higher accuracy, and greater reliability. Solid-state breakers are commonly used in critical applications where downtime is unacceptable. Arc flash protection is another important consideration in electrical safety. Arc flash is a dangerous electrical explosion that can occur when there is a fault in an electrical system. Arc flash can cause serious burns, injuries, and even death. Arc flash protection systems are designed to mitigate the hazards of arc flash. These systems typically include arc flash relays, current limiting devices, and personal protective equipment, or PPE. Arc flash studies are conducted to determine the potential arc flash hazards in an electrical system. These studies involve calculating the incident energy and arc flash boundary for various fault locations. The results of the arc flash study are used to select appropriate arc flash protection measures. Predictive maintenance techniques can be used to identify potential problems with circuit breakers before they lead to failures. These techniques include infrared thermography, vibration analysis, and ultrasonic testing. Infrared thermography can be used to detect hotspots on circuit breakers, which may indicate loose connections or other problems. Vibration analysis can be used to detect mechanical wear or damage to circuit breaker components. Ultrasonic testing can be used to detect internal defects in circuit breaker insulation. By using predictive maintenance techniques, it is possible to extend the lifespan of circuit breakers and improve the reliability of electrical systems. Finally, let's discuss the importance of energy efficiency in electrical systems. Energy-efficient circuit breakers can help to reduce energy consumption and lower utility bills. Energy-efficient breakers typically have lower internal resistance, which reduces heat losses. Energy-efficient lighting motors and other electrical equipment can also help to reduce energy consumption. The National Electrical Code, or NEC, includes requirements for energy efficiency in electrical systems. These requirements are intended to promote the use of energy-efficient products and practices. By implementing energy-efficient measures, it is possible to reduce the environmental impact of electrical systems and save money on energy costs. Therefore, Crouse-Hinds panels can use breakers from Crouse-Hinds, Bryant and Westinghouse.